Okay, so good morning. So today the plan is to compute the canonical partition function for the ideal gas. That's the agenda. And so just let's start with a recap. So we saw that there were two kinds of ensembles. The first one we called microcanonical. And there the interesting quantity was what we called omega of E and possibly other arguments. That was the interesting object to compute, and from that we were able to define entropy, temperature, etc. And the second one is the canonical ensemble. That the object of interest is Z, the partition function, which is a function of temperature. And so these are the two different settings. And so out here in the first example, we saw that the entropy was Kb log omega. We will see a similar thermodynamic quantity which would be expressed in terms of the canonical partition function a little bit later, maybe next lecture. So right now I will not mention it, or maybe I will. We will see that there will be something called the Helmholtz free energy, which will be minus kBt log of Z. Okay, so this is another thermodynamic quantity. We will prove this. We will show this. Okay, so this is, I think, the Helmholtz free energy in thermodynamics. Okay, so we will have something to connect. But today we have something much more simpler to do, which is to compute the partition function for a particular example. But we will see that there are interesting things that happen even in this example. So before that, let's just recall that we gave multiple formulae for the partition function, and I'll write one particular one: sum over all energies for discrete things, degeneracy e power minus beta E. And we also saw, if you write this in the continuum way of writing, we could write this as integral d of E rho of E power minus beta E. Okay, where the summation is replaced by an integral, and rho of, so here g of E was the degeneracy, and rho of E is the density of states. Okay, so are there any questions and comments at this point?
Yeah.
Yes, go ahead.
Yeah. Here the integration is over a finite space or an infinite space?
It's over all, it's infinite. It's so in both cases the sum can run over all possible energy values. So it will go it'll go to infinity. It'll go up to infinity. Okay. Anything else? Okay. So, but this exponential factor e power minus beta E will make this integral convergent in most cases. Okay. So now what we will do is we will write an alternate formula which is equivalent to the second formula. So if you remember, we got integral d of rho of E from was equal to some integral was over all energies in the range E to E plus D. Right? So we can actually use this formula and replace rho of E, this thing, by this integral. So the semi-classical canonical partition function is there a question? Z we can write now. A little bit of thought will show you that. Here F is the number of degrees of freedom. Right? Because energy is nothing but the Hamiltonian evaluated at some point in phase space. So I can replace E by this quantity. Okay, so this is some Z semi-classical. I will not keep writing the subscript. Is this clear? That this formula, at least semi-classically, is equivalent to this particular formula, where instead of putting rho exact, you're going to put rho semi-classical.
Yes, sir.
Huh? Okay. So this is a kind of neat formula, and so let us compute the semi-classical expression. For a 3D particle in a box of volume V in contact with the thermal reservoir at temperature T. Okay, so H here will be nothing but single P square upon 2m. So Z, and I'm going to use lowercase z for this problem because I want to use this expression later, and the Z will be integral d cubed q d cubed P divided by H times e power minus beta P square upon 2n. So we have to do these integrals. This is 6-dimensional integral, but what we can see is that we can do the q integration very easy. So what is integral d cubed V or d cubed Q? Sorry. What is integral d cubed Q?
V.
It's V.
V.
V, and I would put cubed here. So it's V by H cubed integral d cubed P e power minus beta P square upon 2n. Okay, so what I'll write is instead of writing beta, I will write kBT just for okay. So we can do one more part. We can do the angular integration because it's only a function of the magnitude of P. So we can replace this. We can write this V by H cubed. We do the angle integrations. We'll get a 4 pi integral P square dP e power P square upon 2m kBT. So now we can do this integration, and P goes from 0 to infinity. Right, because it's just the magnitude. So we have to do this integration, and this integration we can. So before we do that, let's just change of variables. Let's define p tilde to be p upon 2m kbt power half. Okay, so if we do that thing, 4 pi b by h cubed, and we'll get each of these p's will give, from the measure we'll get 2m kbt power 3 half times integral 0 to infinity p tilde square dp tilde e power minus p tilde square. Okay, so we need to do this integral. Does anybody know what this integral is equal to? Okay, so, or at least tell me how you would go about doing this integral. This is just some number. So we got all the quantities, dependence on everything we got out here, and so we just need to do this integral.
Sir, we have to use the integral form of gamma function, right?
Yeah, we can use
Is
that.
this integral gamma 2?
No, it will be some gamma half, gamma 3 by 2 or something like that. Okay, you have to make, for gamma function is defined in terms of the exponential, so you need to make one more change of variable. So what I will use is really, so the integral of interest is, we can 0 to infinity dp tilde e power some, no, let me write some other variable, just integration, dx e power minus alpha, let's say alpha is some positive quantity. We want to do this integral. This is equal to half minus infinity to plus infinity dx of e power minus, it's an even function, so I can double it and put a half, and this is this integration is equal to half square root of pi by alpha. Okay, so we can, the way to do this integration now is to just do take derivative of this, take minus, take alpha derivative on both sides. Okay, so left hand, so let's call this I. So di by d alpha will be minus integral 0 to infinity dx x square e power minus alpha x square. So you can see that after I take a derivative and put alpha equal to 1, it becomes exactly this integral. But we know this is equal to this guy, so it will be root pi by 2 into minus half alpha power minus 3 by 2. And we have to set this, so this becomes, implies, so we get, this implies that integral 0 to infinity dx e power alpha equal to 1, so I don't need that. Okay, so we get root pi by 4. So this is just a detour. So this integration gives root pi by 4. So coming back to that, so we get z equal to b by h cubed. What was it? 2m kbt power 3 half, right? Integral 0 to this thing, so that will give you, and there was a 4 pi from the integration, so we get into root pi by 4. Sorry. Okay, so the 4's cancel and this pi can be taken inside, so we get v into 2 pi m kbt, and I'll take this h also inside and write it as h square power 3 by 2. Okay, so at least this this formula is true semi-classically, and so we get this answer. Okay, are there any questions and comments? So this is just a simple example.
Sir, could you explain how you got 4 pi and how the limit became 0 to infinity?
Okay, that's easy. So let's look at this point here, right? So p square is just the magnitude. P is just a magnitude. So dqp is dp1 or dpx, dpy, dpz. I can go to spherical polar coordinates, and I can write it p square dp times solid angle d omega it's a spherical polar coordinates in p space, and the omega integration gives you 4 pi, right? Because the integrand is independent of omega, so it's just angle integration. So that is this 4 pi.
Okay, so basically you just assumed it to be a variable integrated over a volume.
Yeah, but that's, I can do that, right? It's just three-dimensional integral, right? I can do that.
Okay, sir, thanks.
Anything else? Yeah, these are simple questions, but you should ask because otherwise it's confusing. Anything else?
So when we write the formula for z as integral dq to the power f dp to the power f by substituting the rho e d, so naively it seems to me there should be a double integral, but somehow that isn't.
Oh no, I mean, I the single integral here is actually is a 2f dimensional integral. It's an integral over phase space. I mean, if I keep putting, I mean, if you come here, really this is 6 integrals, so I should actually put 1, 2, I mean, it gets messy, you see. I have to count. So one just notionally, that's all. So,
thank you.
Good. Yeah, these are notations which work when you have double, triple integrals. When the number of integrals increase, you just put one integral. But if you want to give limits, you want to be more specific, then you put extra integral symbol. So this integral symbol is just a formal symbol that you're integrating over 6 variables. Okay, great. These kind of questions are important because, lots of people have this kind of confusion, which is very simple and can be addressed very easily. Okay. But this is a semi-classical computation. And so we would like it to do it for n particles, so we have to do a 3n dimensional integral, etc. So before we do that, I want to do a second example. Okay, so let me. Okay. Yay. So, life is made up of small victories where, I mean, I didn't want to waste my time doing this, so before class, I actually sat and did this thing. So we will consider a situation where we have 3 particles and 5 states. With energies epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5. I have drawn it in this thing, but I'm not. It could be that there could be degeneracies, etc. So the energy, for instance, it could be that epsilon 1 and epsilon 3 have the same value. But these are distinct states. So there are 5 states, and I have 3 particles, and each of them. So what I have in mind is I have 3 particles in a box, say. So all of them you can quantize. The quantum values for these things. So for each of them, you will say there are 3 quantum numbers. So that way you will get infinite number of states. But I just want to do a simpler example where I have a few more things. I take only 5 of the multiple the infinity things. So and I just decide which there are 3 particles. I just tell you what their energies are. Okay, so I'm doing a very simple example where there are only 5 states. Of course, this is a caricature of reality, but what I want to explain will work even here. Okay, so is there a way to move this? I won't try such things. I just need to copy some more. Paste. Very good. So now let me start showing you possible things. So I'll use particles. I will use them with x. So I could have a situation where one particle 1 is here, particle 2 is in this, and particle 3 is in this. Okay. I could have another situation where there are two particles in this state, and okay, by that I mean their quantum numbers are, so let's look at epsilon 2 associates 3 integers, right? So both the particles have the same, let's say both were in 2 1 1. So that's what this this sort of symbol says. Okay, there's another possibility which I will show now, where all of them are in the same state. Okay, so I'm going to pause here and ask you, is this picture clear?
Yes.
Okay, so they're identical particles, and they're in the same box. So this is what is happening. Okay, so I'll just call these configurations as type 1. Type 1 is where all the three particles are in distinct energy states. We'll call this type 2. And I'll call this type 3. I mean, this is not some standard notation, just I have three possibilities. If I had 4 particles, then there will be a fourth type. And if you have n particles, fourth type, because I can have 3 particles in one state and one in a different state, and I can have all 4 particles in the same state, so on and so forth. I can get all these things. Okay, is this?
Sir, we can just call it as degeneracy 1, 2, 3, right?
No, we have to. There is a little, I mean, I'm getting to what you are saying, but there is some subtlety in this story, and that's what I'm getting at. Okay, so I just want to be very concrete and discuss 5 particles, 3 particles. Okay, that's what I want to do. Okay. So coming back to this thing, so now we can see. So let's ask how many possible. Let's consider this type 1 configuration and ask what is the degeneracy. So I can have particle 1 in epsilon within state 1, particle 2 in state 3, and particle 3 in state 4. So I can do that. But I have 3 factorial ways, right, of doing that. If the particles were distinct, right? I mean, so degeneracy, there will be 3 factorial ways this can happen. There are 3 factorial configurations because we want to work out the degeneracy. Right? Hello? Is this computation of 3 factorial clear?
Sir, isn't it 5 into 4 into 3?
No. I'm fixing the energy. The energy of the state is fixed, right? It's epsilon 1 plus epsilon 3 plus epsilon 4. So this
Okay.
Right? And for this purpose, we'll assume they are distinct numbers and such that they are incommensurate. So any addition, there's only unique combination. Okay? So then it is 3 factorial. Yeah, what you're saying is if I choose 3 things which could come, there are these kind of states of type 1. That's what you're saying. That is correct. What about type 2?
Yes.
What about type 2? It's 3 factorial by 2 factorial because there is a degeneracy. I mean, 2 states are there. So this will have only 3 factorial by this. I'll just write it 3. How about this?
Just one way.
There is 1. Okay. So is this computation of 3 factorial, 3, etc. clear to everybody? So this is important. Okay. So let's now do this computation. Okay, so we would like to compute. But there's a simple way of doing this. Is that let me just define little z is just for one of those particles in any of those 5 states, and then for that it is just e power Okay, you agree? If there's just one particle and 5 states, what is the partition function? This is what you would have written. Okay, now if you look at z power 5, sorry, z cubed, okay, and look at its expansion. Okay, so you will find, for instance, so let's look at how a term like this will come. Epsilon 1 plus epsilon 2 plus epsilon 3. You will see that that will have 6. What was the things? 1, 3, and 4. Plus there are other type 1 terms. I am looking at only these 2 type 1 terms. All these terms will come. Type 1, type 2, type 3, all terms will come. And then this one will be epsilon plus 2 epsilon 2.
So that
1 second.
superscript of 3.
Yeah, go ahead.
So that superscript of 3 represents just the 3 particles.
Yeah, so yeah, exactly. So what I'm saying is, what I wanted to say is that taking the third power of this will capture all those things. All possibilities will come. If I take little z and take its cubed power. The binomial coefficients, so will work out correctly.
Sir, shouldn't the second term be multiplied with 3?
Yeah, not 2, 3. Thanks. Yes. Okay. So plus these are type 1 terms, type 2 terms, and type 3 terms. Okay. So now we can conclude that z cubed gives the partition function for 3 distinguishable particles. Right? You can go back and check, you can expand and see for yourself, but it's just standard binomial theorem, generalized binomial theorem, which will give you this fact. Okay? Is this acceptable, what I'm saying? Okay.
Yes, sir.
Okay. However, this is not an interesting computation. In reality, particles are indistinguishable. Okay, so what I mean particles of same type. Okay, suppose you have a mixture of hydrogen and oxygen. Okay, what I'm saying is all hydrogen atoms will be indistinguishable and all oxygen atoms will be indistinguishable. So we are looking at only one species out here. So particles are indistinguishable. So now the question is, you come back to this thing and ask, now if you ask what is the degeneracy, I'm going to write the degeneracy in yellow. This will become what? How many configurations are there if they were indistinguishable? 3 factorial becomes what?
By 3 factorial.
Yeah, so it becomes 1. This becomes, there's only one configuration. You give me the energies and you get 1. So again, this goes to 1 and this goes to 1 when it is distinguishable. So this is for distinguishable. So what we see is that z cubed, now z cubed doesn't work. When, let's just make this lowercase, when particles are indistinguishable, z cubed does not work. Okay, is this point clear? It gives the wrong prefactors. Okay. Okay. Then, however,
Sir,
Yeah, go ahead.
Could you please repeat this? When particles are indistinguishable, Z cube doesn't work.
Yeah. So let's look at type 1, which is the best situation. So how did we get 3 factorial? We said, particle 1 is here, particle 2 is here, particle 3 is here, and all permutations. But the whole point here is you can't name when the particles are indistinguishable, you can't name them like you name your cat or dog, right? If you have 3 cats, you can name them A, B, C. Okay, and they are clearly distinguishable and they are individuals, right? So, yeah, but if they are indistinguishable, these are microscopic particles, and quantum mechanically they are truly, even if you think that you give them names, what you will find is that when they come close enough, you will lose track of what they are. So they are actually truly indistinguishable. Okay, so that's actually a quantum mechanical fact. So all I'm saying here is our 3 factorial counting will be replaced by 1 if they were indistinguishable, because you can't tell whether particle 1 is in state 1 or particle 2 is in state 1 or particle 3, it doesn't matter. They're all the same. So this 3, what we associated degeneracy of 3 factorial is now actually 1. That's what I'm saying. And for type 2, it was 3 becoming 1. Again, it doesn't matter. So have I answered your question?
Yes.
Okay, good. So all I'm saying is that Z cube worked very nicely if they were distinguishable. But however, Z cubed power 3 factorial gets the count or the degeneracy. And is wrong for type 2 and 3. Because for type 2 it will give half instead of 1, and for type 3 it will give 1/6 instead of this. Okay, is this point clear?
Yes.
So now we need to move beyond this. To the case of n indistinguishable particles. And of course, and an infinite number of states also, both. Okay, so where n is much greater than 1 here. Okay, remember that. So now the question is, something interesting happens in this case. Configurations of type 1 dominate, because there are so many states, and if you're trying to put particles, and number of states is much, number of particles, even if you say it's 10 power 23, it's still much less than infinity, because there are infinite number of such configurations, and that configurations of type 1 dominate, and so little z power n divided by n factorial is a very good approximation. Okay. Okay. Again, there is a situation even when you have something like this, is that if you go to 0 temperature, things will settle down, and states which are at higher energies, they don't contribute. So effectively, because of the weight factor, only states which then in such situations type 2, type 3, etc. will start contributing, and so then this approximation will break down. But okay, let's say we are looking at reasonably high temperatures, okay, at least at high temperatures. High means need not be like very, very high, but not close to zero. Okay, so now what we have is a partition function. So Z so we already computed, so now we are ready to write. So for an ideal gas with n particles, we can use this method. We get Z equal to little z power n divided by n factorial, where little z is what? V times something we had written. You would remind me, 2 pi mkbt divided by, is it h square power 3 by 2. Okay, so now we got a formula. Now we are in business. We have computed. Also remember, our semi-classical formula is expected to be valid only at higher temperatures. So everything is sort of nice. So we have a formula for the canonical partition function of after all this. Okay. So is this point clear? Okay. So, but of course, this guy gets the. This one gets the. This is only an approximate partition function, and just I want to make one more remark. And this is so fundamental particles come in two flavors. They are called bosons and fermions. And fermions have this special property that there's something called the Pauli exclusion principle, which says that two identical particles cannot have the same, all their quantum numbers shouldn't be the same. They cannot be in the same state. Okay, so here, so I will write now for you so implies that if you have a gas of identical fermionic particles, then configurations of type 2 or 3 are not permitted. Okay, fermions have additional quantum numbers, spin quantum numbers, so we have to put them also into the story. So for now, we'll just ignore that, but we'll put in Pauli exclusion principle. Let's come back to this picture that we had. Why is type 2 not allowed for fermions?
Because second energy state contains two particles.
Same thing with 3. So only, so so are not permitted. So Z only from only type 1 configuration. Okay. Also, for bosonic particles, type 2, type 3 are allowed. Okay. However, Z power n by n factorial is only an approximation, because as I mentioned, you're getting for type 2, type 3 the configuration. Okay, again, so here also okay, so for both of them this Z power n by n factorial is an approximation, but what we will find is that some parts of the physics is gotten right by just dividing by this n factorial, and this is a semi-classical value. Okay, so I'll pause here so that you can ask questions or comments, and then we'll take it from there.